This lecture is about planned contrasts and post hoc comparisons, those tests we have to do after obtaining a significant F value in an omnibus F test. We don't know what the significant pairings are, so we have to do additional tests. So the F ratio is what we call an omnibus conclusion. Omnibus means sort of it's an umbrella conclusion. So in the case of the F ratio, it tells us that the variance between the groups is greater than we could explain by the normal variance within the groups. Again, that thing where we don't expect it by chance. And we call it omnibus because it's about all the groups. We don't know anything about which pairs are significant. And usually, though, we're interested in the difference between particular groups because we have some hypothesis that led us to do the study in the first place. So the F ratio is limited in what it can tell us. It just tells us that the variance is greater than we expect. So we have two approaches to find out which groups differ. We can first plan in advance. And what we would do then is do what's called planned contrasts, which are comparisons between specified groups that we plan out in advance. And so in that case, we might have, in our juror example, a hypothesis that those people who find out that the defendant has a previous conviction might be more likely or find her more guilty than people who thinks that she has no conviction. But we're comparing three groups. We're comparing those who think that she has a criminal record with those who think she doesn't have a criminal record with a control group. So in order to find out which of those groups are significant, we have to do more tests. So these planned contrasts are called a priori comparisons. That just means in advance. It's a good way to conduct research because it means that you have a good theory that's leading to you to do the study in the first place. And so you wouldn't plan to do contrasts between all the pairs, but just the pairs about which you have a theory. On the other hand, sometimes there's not a plan in advance like that. Someone might be conducting more exploratory research, and in that case, they would just wait to see if they got a significant omnibus F ratio. And if they did, then they would compare, have to do like a fishing expedition and compare a whole bunch of pairs to see where the differences lie. So it's exploratory. And because it's not planned in advance, it has to include all possible comparisons. So going back to planned contrasts, in that case, we would calculate an F ratio for the two groups of interest. So we would do this after getting a significant F observed score in the omnibus test. But then we would do additional F tests to see which pairs are similar. We'd only test the ones that we hypothesized to be different, and we would use the very same MS within that we calculated for the omnibus F test, but we would calculate MS between just for those two groups of interest. And so we would get that F ratio for just those pairs, and we'd do maybe two tests if we had two planned contrasts. We do have to be aware of a particular problem, though. Just like the more lottery tickets we buy, the more likely we are to get a winning ticket. Likewise, the more tests we do with a single data set, the more likely we are to get a spurious result or a type 1 error result, a statistically significant result that actually is a false positive. And so Bonferroni has a correction that we do to address the problem so that we can still have 0.05 likelihood of a significant result, even though we're doing multiple tests on the same data. And it's just a simple calculation. We divide alpha by the number of planned contrasts. So if alpha is 0.05 and we have two planned contrasts planned, we would divide alpha by those two tests we intend to do. And then we would use that corrected alpha, as well as the new degrees of freedom for those two groups only, to find our cutoff point. So here is our juror study. We have planned contrasts. We're going to compare condition 1, which is those jurors who were told the defendant is guilty. And we're going to compare them with condition 2, those who were told she's not guilty, and with condition 3, who were told nothing at all. So we're going to use the MS within as the denominator. We had a 5 there. And then the numerator, we're going to calculate a new MS between. Here's all the math for that. We won't worry about looking at all this now because we'll be looking at it in the demos. But we should look at this little cutoff point right over here in the corner. And so the cutoff point is where we're going to draw the line. We're looking for a sample F score higher than that cutoff point to have a significant result. But we have to have a more stringent cutoff point because we have to take our alpha of 0.05 and divide it by our 2 tests, which means we actually have to enter it as 0.025. So now we're looking for an observed F score that has only a 2.5% of occurring by chance. And then we would use that new degree of freedom using our cutoff point calculator tool. We would use the new degrees of freedom to find out what the cutoff point is. In post hoc tests, they're actually the very same process, but they have a little bit different rationale and approach. So post hoc tests are tests where we run an analysis of variance and get a significant result, but we don't have any particular hypothesis about which pairs will be significant. So we don't have any a priori or advanced planning. So there are many kinds of post hoc tests that we can do, but the two that we'll talk about today are the Tukey's test and the Scheffé's test. So in the Tukey's test, we compare all possible pairs. And so we would definitely make sure of the Bonferroni correction. So for example, if we have 3 conditions A and B and C, then there are 3 possible tests for the Tukey. We'd have to do all 3. We'd have to compare A with B, we'd have to compare A with C, and we'd have to compare B with C. And we'd have to take alpha, 0.05, and divide it by those 3 possible tests, meaning that we'd have to get a significance level that has only a 1.67% chance of occurring. So we're going to have a fairly high F cutoff point. Another kind of test we can do is the Scheffé's test, and this is even more statistical test because we don't just compare all possible pairs, we compare all possible configurations. So it allows us to compare both combinations and pairs. So for example, if we were going to do the Scheffé's test, we would have to do all of these 3 already listed, A versus B, B versus C, and A versus C, but we'd also compare A plus B versus C, A plus C versus B, and B plus C versus A. So that is 6 tests, so we'd have to divide our alpha by all those tests. Alpha 0.05 divided by 6, that means we're looking for a cutoff point that has only a 0.833% chance of being obtained just through a random fluky sample. So we're really getting a stringent cutoff point if we do all of these tests. We can display ANOVA results in many different ways, but one of the most common is through what we call a box and whisker plot or a box plot. You'll see these a lot in research articles. The box in the middle represents what we call the interquartile range, or the middle half of the data. So 25% of scores will be below the lowest level, and 25% will be above the highest level. The dark line in the middle that you can see more easily in these light colored boxes will often represent the median. Sometimes it represents the mean, and you'll have to look up to see which it is. And this gives the viewer some information about skew. So in this example of this 4th bar over where the mouse is hovering, we have the middle 50% of scores, but we can see the median in this case is, quite down toward the lower end of those scores, which suggests that we have a skewed distribution. These lines extending from the boxes represent we have to read the notes to know for sure, but often they represent the minimum at the lower end of this and the maximum at the upper end. Sometimes they can represent the 95% confidence intervals with 5% of scores below here and 5% of scores above here. Dots on a box plot represent outliers. So in this last bar over here, we have 1 outlier that's low and 2 that are high. This is another example of a box plot, and I'll talk in this slide about how we can at least get an idea of what might be statistically significant by looking at a box plot. So we can't tell for sure what's significant without running a statistical test, but we can get a clue. For example, if the boxes don't overlap at all, as we see here between Friday and Thursday, you can see this box interquartile range does not overlap at all with this box. This is very likely to be a significant result. In fact, these Wednesday-Thursday scores are probably significantly different from Friday and Saturday scores in both cases. And if we looked at a box plot, sometimes researchers will indicate that through these brackets. So this one is pointing to the Friday score and the Thursday score. The two asterisks above represent a 0.01 level of statistical significance. And we might see another one showing that Wednesday is significantly different from Friday. And we might see 3 asterisks, meaning that the probability is less than 0.001. We can also understand that sometimes the boxes can overlap, but if the mean or median in one is outside of the interquartile range of the other, there's also a good chance of significance. And we can see here, comparing Saturday and Sunday, that the mean for Sunday appears to be maybe lower than the box for Saturday, and the mean for Saturday is certainly higher than the box for Sunday. So even though these boxes interlap, this still might be significant. And that would be indicated in the same way, maybe with 1 star, indicating 1 level of statistical significance. These bars don't have to be adjacent to each other. The statistical test will tell us whatever two are different. You know, if we do post hoc testing, we'll find out whichever two are different. They don't have to be adjacent. Once again, we have to do statistical tests in order to be sure. Another way to display ANOVA results might be through this bar chart. In this case, we see the 3 bars, and the top of the bars most likely represent the mean. There are typically notes underneath the bar chart that will clarify these things. These little T-shaped indicators above the bar likely indicate the standard error, or the SM, that we have used for our calculations. And these lines, just like in the box and whisker plots, are showing us significance levels. So the red bar and the green bar are statistically significant at the 0.05 level. That's what the 1 star represents. And the black and the green are significantly different at the 0.05 level also. This repeats the information I just gave you. And the norms for the stars, asterisks, 1 star, in a graph or anywhere typically means that the probability of achieving this result is less than 5%. 2 asterisks means that it's less than 1%, and 3 means that it's less than 0.001. This is another type of chart that I'm not going to talk to you about because it's not frequently used. It's called a bee swarm chart, and it does show every single data point plotted out so you can see exactly how the data points are laying in comparison to the others. So in summary, ANOVA is used to compare means when a study has more than 2 groups or conditions. One variable, one way ANOVA has 1 variable, but more than 2 groups. ANOVA provides an F ratio comparing variation between the groups with variation within the groups. The F ratio is an omnibus figure or an umbrella type figure telling us only whether the group variance differs more than the variance within the group. We have to conduct more tests after a significant ANOVA to know which pairs or combinations of pairs differ significantly. We can do planned contrasts, a wise approach, planning a priori based on theory behind your study, or we can do post hoc tests, and they're tending to be more exploratory, and they have to include all pairs or all combinations. We can't pick and choose just the ones that look like they might be significant. We do have to take alpha and divide it among the post hoc tests or the planned contrasts in order to avoid having a greater than 5% likelihood of obtaining a significant result.